recording is on. What did we said in the last lecture? We talked about Riemann sums. Let f be a bounded function in a segment AB. F is called integrable, meaning it has area between it and the x axis. If for every sequence PM of partitions, which geometrically, intuitively speaking, gives us the basis. I can minimize this as well. The basis of the rectangles. With lambda, favorite letter, tends to 0 when m goes to infinity, which means that the bases are getting smaller and smaller. And for every sequence CM, oh, we called it point choosing. That represents the heights of the rectangles. The Riemann sums we denote by SR of F, P, M, and CM, and are actually the sum. I goes from I to 1, FCI, delta xi, where delta xi is xi minus xi 1. Are all have the same limit. In such case, divided with the capital I, the limit, this limit or that limit is denoted as the integral from A to B. And we did two simple examples, one for a constant function, which is integrable, and we calculated the integral, and the second is Dirichlet function, which was not integrable. And we finished with an equivalent condition for integrability. We denote with omega I Hebrew. This is Hebrew. Omega I, the difference between the supremum of F in the I subsegment and the infimum of F. It should be in, right? It's called the oscillation. So you write it in the subsegment xi minus 1 xi. We said that f is integrable, meaning all the sums go to the same limit. Integrable if and only if for every sequence of partitions PM with a parameter that goes to 0. You can delete the parentheses. The partitions with we have that the sum of the oscillations and delta xi goes to 0. And we explained it in the last lecture when we finished it. We didn't grossly mathematically proved it. We mentioned why. So this is a reminder for our last lecture. What are we going to do today? Two things. First of all, I want to write down some of the properties of the definite integral. Linearity and it is monotone and other properties. For every property, we'll explain intuitively why is it true, maybe give some counterexamples to similar properties that do not occur when it comes to integral, a different integral. And that's the first thing. The second one is we'll have a theorem stating that every continuous function is integrable, every monotone function is integrable, and as much as we can do in our, what's it, 70 something minutes, we'll prove this theorem. Okay. So no, no. Let's start as a fresh new subject. Properties of the definite integral. So let f and g be integrable functions in, let's say, AB. Integrable is, again, bounded, and all the sums acts nicely, tend to the same limit. Okay, first of all, integral is linear. Linearity for every, I don't know, sum A in R, the function AF plus G is integrable. And we have integral. No, it's not a good letter because I already used it for the integral itself. So let's say C. No, let's have some alpha. Integral from A to B of the function alpha f plus G is, writing it surely without the dx and the stuff, is the integral of f multiplied by alpha plus the integral of t. I'm not going to prove it. Maybe. His own decision is a big boy, as I mentioned before. Near put it in the homework. But I want to explain why is it true. And remember, we have our spoiler, the connection between the definite integral and the antiderivative f. The indefinite integral, it's fb minus fa, everything is true. But right now, these two notions are totally different. This is the area between the function and the axis. This is the function that if we derive, we get the original one inside the integral. Why is it true? First of all, let's write it down in another color so that proof. It's an explanation. We used purple in linear algebra. We can use different color now. Let's have brown. Brown. First of all, if f and g are bounded, they are because they're integrable, bounded, then you multiply by some scalar, you add two functions, sum them up, it's still bounded. Well, secondly, looking at the Riemann sums, secondly, if you look at the limit of the sum, the Riemann sum of alpha f plus g at some point ci, both the sigma operation and the limit operation are linear, meaning that we can put alpha outside and we're missing the delta xi, fci delta xi plus the limit of gci delta xi. And we know that f is integral. We know that g is integrable. So these two sums are going to the same limit. I mean, all the sums of f go to the integral of f, and all the sums of g are going to the integral of g. So it does converges to this. And this is the integral of alpha f plus g, the limit of all the Riemann sums. I mean, one needs to write it more precisely, all the length and the fancy words, for it to be a nice proof, but that's the explanation. Yeah.
I don't understand. We haven't even really defined what the integral from A to B is. So how can we use it?
The integral is the limit of all the Riemann sums. Once all the Riemann sums converge to the same limit, this is the integral. That's how we denote it. That's practically the definition. The limit of all the Riemann sums.
Right, and that's different to the antiderivative.
Yes,
which is
right.
Indefinite.
Yes, right now it's completely different notions.
So we've just defined definite.
Yeah. And right. On lecture number 6, Bezrat Hashem, next Sunday, we'll finally see the connection. The theorem that connects the definite integral of a and b and the big F, that derivative on the other side. So that's our first property, the linearity of the definite integral. Second property, the integral is monotone. Definite integral is monotone. What do I mean by that? If fx is smaller than gx for every x in our segment, then the integral of f is smaller than the integral of g. First of all, it makes a lot of sense. We know intuitively that the integral is the area between the graph and the axis. And if we have two functions, one above the other, so yeah, underneath the bigger one, we're going to have more area. Secondly, one can write it down using the definition with the Riemann sounds would it be? No, it's not brown, but because f is smaller than g, You multiply it by delta, it's something positive. It doesn't change the direction of the inequality. Sum it, you put limit on it. All these actions on f and g, they do not change the basic inequality. F is smaller than g. And so the integral of f is smaller than the integral of g. One can write it down. Let's put it in brown as an explanation and not some proof. Again, maybe near, no, if in the practice itself, but probably, or if you're gonna do it, so probably the homework, use some of these properties to actually prove mathematically, not just the explanation, but it goes like this. Let's just write we have or something like that. So, specifically, two things I want to write down. Specifically, that's how you write it. Do you have an A here or not? Specifically or specifically? How do you write it?
But I think it's double A. No.
No,
Double L.
double F, no.
Double L, like this.
Double L. That's right. It's a lot of letters. Well, as Google. Yeah. Specific. Yes, it's double L. It's double L. You were right. Good. Specifically, one, if f is greater than 0, and for every x in the segment, then the integral is greater than the 0. I mean, it's greater than the integral of 0, which is 0. And yet again, it's very making a lot of sense if the function is above the x-axis, the area is positive. Secondly, we know that f is bounded. Yes, so there are little m and big M such that f is bounded between them. It's not what I want to say. It's the one of it's given to us. I mean, f is integrable, so it is bounded. And so the integral of f is bounded between the integral of little m and big M. And the integral of little m and big M, we know what is it. We know what they are. We calculated it on Sunday. Integral of constant function is the function multiplied by b minus a, by the length of the segment. So we have m b minus a and m big M b minus a bounding the integral.
This
What?
doesn't go the other way.
If the integral is bounded, it doesn't mean that f is bounded, right? We can't have it. Because when it comes to integral, it can be very small because the positive area above the axis and the area, the negative area under the axis just cancel each other. One can, let's do it. One can show it geometrically. Yes. With the A between the double L. Yeah. No, I don't want to write down this. It's gonna be if I know what you're thinking, it's gonna be my third property, but now right now we are on the second one.
You're coding.
Yes, we have A and B here, and some function. No, it's too high, close to the text. Okay, let's say that's the function f, very nice one. And we have here, let's say the small m level, which is the minimum of the function. And we have here, write down yellow, blue, the big M level of the function. Now, we have the rectangle of big M B minus A, which is all the blue area. And we have the rectangle of small m B minus A, with this little one down here. And it's easy to see that both of them are bounding the actual area, the integral itself, which is the black one. So the area itself of f, of the integral, is bounded between these two rectangles and their respective areas. I'll just plug it in as a PNG. Then we can move on. Now for your probability, one can ask, fair question. If we start at little m and we go up slowly, we eventually end in big M. Is there a point throughout the way in which the rectangle, the area of the rectangle, is exactly the same as the area itself? I mean, we can move upwards slowly and look at this rectangle and this rectangle, etc., etc. Now, by the not mean value, the second one, the intermediate value, that's what we call it.
Yeah.
The intermediate value theorem, we know that there is some point between, on the y-axis, between little m and big M, that gives us a rectangle with the exact same area as f. Is not big deal. What is more interesting, is there any point on the graph itself that gives us a rectangle with area as the same as f? As we know, the intermediate value theorem requires continuity. F should be continuous. So it's the same here. One can call it the integral intermediate value theorem. This would be already written down, right? Right. Yes. So that's our third property. Integral intermediate. Let's write it. I'm not sure. Intermediate value theorem. If f is continuous, there is a point C between A and B such that the integral, which is the area, is FCI multiplied by B minus A, which is the area of a rectangle with basis, the segment AB, and height FCI. And as in the regular intermediate value theorem, we need f to be continuous. We already drew, let's write it in past. So you drew the rectangles, we can say that. Any questions? Okay. I'm going to use it in my proofs, not today, but probably on Sunday. Fourth property. One can call it additivity, חיבוריות בעברית, of segments. I mentioned you f is integrable. We know it. It's bounded. Know it. Now, for every C, Control N, Control that, Control S. For every C in A and B, F is integrable in A to C and in C to B. And we have the whole integral from A to B is the sum of the integral from A to C and the integral from C to B. What? Yeah, because we didn't. On one hand, by our definition, it should be a segment, which means B is larger than A, and if we talk about A and C and B, C is larger than A and B is greater than C. Yes. On the other hand, one can think, and we will actually write it down in the next lecture, one can think of the integral from point to itself, from A to A, as zero, because the area underneath one single point is zero. But we write it as a definition or as a property of integral in our next lecture. So right now, yeah, write it down as an open segment. C cannot be A or B, but mathematically speaking, it's not so bad. If we consider C to be A or B, it will work as well. So as I say, it makes a lot of sense as well. We can calculate the whole area from A to B by parts, from A to C and then from C to B. And of course, if F is bounded on all the big segment A to B, it is bounded on AC and AB and CB, etc., etc. So that's our fourth property.
The area of one point is zero, and then adding all the areas of zero under the infinite amount of points between A and B gets us.
You said it. You said it. It's infinite. When it comes to infinity, all
it's infinity times zero.
Yeah, but it's infinity. So all the things we know not necessarily apply. Applies. I mean, we know it from series from our first course. If we sum one above n, one and half and third and quarter, etc., etc. So everyone tends to zero, but the whole sum not just converges something deeper than zero, it's actually divergent. It goes to infinity. Because
like Venus paradox.
Yes and no. I mean, I don't think one can argue Zeno was, I don't want to say stupid, but man, you can just walk the 2 meters, just for 2 steps. This is something different. It is approaching infinity in the right way, not in the premature way of Zeno. And it is complex. It is complicated, of course. We have two basic courses in infinitesimal calculus 1 and 2. And they don't give the whole picture, of course, of infinite. I don't think one can give it. Okay, philosophically speaking, this is our fourth property, and our last one, I call it the triangle inequality, but for integrals. Remember, f is integrable. First of all, I'm saying that the absolute value of f is also integrable, which is not trivial, but on this you should believe me. And integrable, and we have the absolute value of the integral of f
In segments or generally?
we have f integrable in the segment AB. First of all, I claim that the absolute value of f is also integrable. It's not.
I mean, if you can do it by segments, you can do like for every cross to negative.
Yes, but if you have the infinity number cross,
Okay.
it's not that simple. But you should believe me on this. And secondly, the integral of f is bounded by the integral of the absolute value. This does make sense because on the left side of the inequality, first of all, we calculate the integral in which positive areas and negative areas can cancel each other. Meanwhile, in the right side, I don't know if you see the absolute value clearly. I mean, I can do it like that, which is better. On the right side, we first apply the absolute value, meaning we don't have any negative areas anymore. They're all positive and they do not cancel each other. On the contrary, they add up. Let's write down a simple example. If we can draw a simple example. When it comes to a formal proof, one can write down the sum, and this is the actual triangle inequality. When it comes to sum of absolute value or the absolute value of the sum, which is bigger. But here we can have some nice little drawing. Let's say we have the function is sinus x. The segment is 0 to 2 pi. Don't look for right proportions or precision. I want to show you the principle. This is sinus x. The area, our signed area is actually 0 because the hill and the valley just cancel each other. And the absolute value of 0 is still 0. Now, if we look at the graph of the absolute value of sinus x, what, geometrically speaking, the absolute value does, it takes the values, everything beneath the axis, and just put it up, mirror it. If we look at the axis of the mirror, let's write it down with a different color. I have pink. This is the absolute value of f, the absolute value of sinus x. Now, we don't know yet how to actually calculate it because we did a spoiler, but we don't actually see in here and proved the theorem that connects this and f, big F. And one can use the cosinus in 2 pi minus the cosinus of 0, etc. But here, you trust me again, you get 4, which is, of course, greater than 0. And yet again, it's common sense. Here, on the left side, things can cancel each other, and here they just add up. Okay, let's clear all the drawing and paste them back as PNG. Actually, the scale it's gonna be very ugly when I PDF it. Let's think. 7 is fine, and here 16. Yeah, I think 7 is fine as well. Let's do it. Okay, that's our fifth and last property of integrals. We're going to use them in our proofs. I don't know how many times we're going to use them today, but next Sunday, we're going to use them for our proofs. Okay, that's our first part of the lecture. Any questions? So the second part, as I mentioned, is one nice big theorem. I mean, it's three or four, two theorems that I combined to one. Let F be a bounded function in AB. First of all, if F is monotone, then F is integrable. The opposite direction is not true. Not every integral function has to be monotone. Secondly, if F is continuous, then F is integrable. If F is continuous, we know that it is bounded by Weierstrass theorem. So the condition for bounded is not needed for the case of continuous function. It actually happens automatically. But I write it down as one big theorem, so that's our first, that's a basic start, or basic given point. And C, if F is bounded, has a finite number of אי רציפה in continuity.
Yeah, I'm gonna be on it.
Yes, when the function is not in continu. What? I'm lost. Continue. It is like this,
Yeah.
plural, in continuities. I'm missing some n, no?
What?
Am I not missing some n? In continuities, is it? Continuity?
Yeah.
So continuity.
Continue. Continues.
Continuity. Okay, sounds right. Sounds right.
Takes a spell check.
Yeah.
In
Huh?
continuity.
Leaks must have a spell check. There's no way that.
It does, but I mean the basic format of the file is Hebrew one, so we don't think it can spell check the English words. Yeah, it sounds fine. Okay, it is, and it is bounded. Then F is integrable. C is just a generalization of B, which has 0 points of incontinuity. Okay, so that's our big theorem. Right now, we still don't have a nice theorem for calculating the integral. This will be the theorem next Sunday with the big F, but it is good for knowing that function is integrable. And when we know that function is integrable, we can choose a specific sequence of partitions and a specific sequence of point choosing in order to calculate the integral. Because integral means that for every sequence of partitions you take, for every, with the parameter goes to 0, for every sequence of point choosing you take, you get the same limit. And of course, using the F gadol, big F, calculate the integral is much easier than choosing a sequence of partitions and sequence of point choosings. Okay, so as I said, we're going to use the rest of our class, the time we have, to prove this theorem. If we keep it in a good pace, we'll prove A, B, and we'll explain how do we prove C. which is generalization of B, so it's not very different from the proof of B. Okay, proof. We have proof A. Let's write it down. It's gonna be a long journey. We use the equivalent condition for integrability using the oscillations. Let PM be a sequence of partitions of the segment AB with lambda PM goes to 0 and M goes to infinity. We need to show that the sum of omega I delta xi tends to 0 as M goes to infinity. As we mentioned today, and we explained on Sunday, it is equivalent to integrability. So how do I do it? How do I use the fact that function f is monotone? Here it A, prove A. Let's space it out a bit. We could have said it last lecture, but now it's important, so I'll say it now. The sum of oscillations is always positive, or at least non-negative. An oscillation is always non-negative. It's the sub minus the inf, and the inf is smaller than the sub. And the deltas are positive as well. They are representing the length of the subsegments. So, because is greater than 0 by the sandwich rule, that's what I sandwich. By sandwich, it is enough to show that our sigma is bounded by some expression, by something that tends to 0. Don't have to work with the expression itself. We can look at the greater, probably more simple expression that goes to 0. And sandwich will give us that the sum itself goes to 0 as well. So what do we look at? We know that the parameter of the partition is always greater than the lambda xi, because the parameter is the maximum of all lambda, of all the lambdas. It's the greatest, the largest subsegment. So if we change lambda xi for the parameter, we get something bigger. Again, everything here is positive, or at least non-negative. So
Here.
lambda here, lambda there, lambda everywhere. But this is not, no, it's not my convention's choice. I can choose a different letter, but that's the common custom. The lambda PM is something, is a constant. Considering the sum of omega I, so I can put it out from the sum. It's always positive because it's the largest of all length of the subsegments. Every delta is positive because it's length of some segment. And now we know that lambda PM tends to 0. That's by definition of our sequence of partitions. So lambda PM goes to 0. So it is enough to show that the sigma omega I is bounded. You multiply something bounded with something that tends to 0, the multiplication tends to 0 as well. One of our basic propositions of infi 1. And so it is enough to show that the sum of omega I is bounded. And here I use the fact that the function is monotone. Monotone or monotonic? How do you say it? Right, monotone, whatever. You understand that one. Function is sigma is bounded. Let's first let's write it down explicitly, and then can explain why. We write down that's an important rule when it comes to solving and understanding mathematics. When the sigma is confusing, you write it down explicitly. Without the sigma, most of the time, it will help you understand what the hell is going on. We write it down explicitly. Here's just 1L. Sigma of omega I. Let's add some indexes so we have something to refer to. The sigma of omega I is omega 1 plus omega 2 plus omega 3. We can write down that way. Omega n, and every omega is sub minus inf. Sub minus inf. We have sub xfs x1, x0, x1 of f minus the inf. That's 1 omega. I don't know what I did here. And the second one is the sub in x1, x2 minus the inf in x1, x2. And so on, and so on, etc., etc., etc. And you get to the sub of xn minus 1, xn, the last subsegment, minus the inf of xn minus 1, xn, the subsegment. And now, what can we say about a monotone, monotonic, whatever function that we cannot generally say? Let's assume the function is increasing, okay? The proof for the decreasing case is the same. Assuming function f is increasing, we can say the following thing. Let's write it down. It's a very little drawing. Don't need actually to keep it in the PDF itself. It's not a monotonic function. It's not good. Let's look at some segments and draw the function with different color. That's a monotonic function. Specifically, I write it down that way. It is not continuous. It is some jump point. It's all fine. It's a continuous function. It's a monotonic function. Because it is monotone, forgive me this little start here. Because it's monotone, the sup of every segment, which is intuitively the right hand of the segment, the right end of the segment, is smaller than the inf in the next segment, because the function is always increasing. All the values in segment 2 are larger than all the values of f in segment 1, which means specifically the inf of f in segment 2 is greater or equals the sup of f in segment 1. Let's write it generally and conclude what I want to say. Because f is increasing, fx is greater than fy for every x in some subsegment, let's say xj minus 1, xj, and let's write this is y and this is x in the next subsegment. The function is increasing because every y in one subsegment is smaller than every x in the next subsegment. The function behaves respectively. Fx will be larger than fy. And so the sup of f in the segment xj minus 1, xj is smaller or equals the inf of f in the next subsegment. Again, intuitively, it's just the values on the ends of every subsegment, because the function is on its own, but we don't know if it's continuous. So write it down that way. I missed the bracket here. Which means that the difference between them is not positive. Now, we can rearrange the components of the sum in the following way. Change the order of the elements of the sum. And I arrange it that way. Every sup goes with the infimum of the next segment. So we have sup of x0, x0, x1 minus the infimum of x1, x2. And the sup of x1, x2 with the infimum of x2, x3, 3, etc., etc.
Sorry, what are we trying to prove here?
That this sum is bounded. And what is bounded, multiplied by something that tends to 0, it will tend to 0 as well. Which is enough for us to prove that the function is integrable.
Uh, and again, little omega is the oscillations between the
Sapadiv, the supermom infimum in every segment. But now we arrange the sum a bit differently. So every supermom will meet the infimum of the next segment. And as we explained, every such difference is negative, or at least not positive. So we can move on and have the sap of the x minus 1, xn, no, xn minus 2, xn minus 1 before the last segment, and the infimum of xn minus 1 and xn, the last infimum. And besides, we have on one hand the infimum of xfsx1, who does not have a partner. The sub of the previous segment does not exist because it's the first segment. And on the other hand, we have the supremum of the last segment. It doesn't have a partner as well. It should go with the infimum of the next segment, but this is the last one. So, besides these differences in our summation, we have sap of xn minus 1 xn without any partner, without friends. And the font is large, the board is small. What are we going to do? If you already write it down, I think I will give up on this component. So it will all go in for one line. Minus the infimum of xfsx1, which don't have any pattern. Now, every one of the differences in the brackets is negative, or at least not positive, as we explained. So if I just delete them, I'm giving up on some negative components, the sum just getting bigger. Mean shows every one of them. Let's write it down the fancy way. Where is it? Oh, it's here. And say, hey, this is larger than, oh, it is smaller than 0. And every one of the differences smaller 0. So if we just give up on them, let them go, we get something larger, greater, bigger. Now we know that the function is bounded because it's one of those what's given to us in the first place.
We already proved that that is completely different.
What? This difference?
Same thing at the end.
This one?
Yeah. Roll that down and said.
Yes, that's our sigma of omegas. We write it down explicitly and then changed the order of the components, and we got this. These are sigma of omegas. Now, I want to show why there exists some bigger expression that tends to 0. So by sandwich rule, it will tend to 0 as well. I just give up on every negative element here and every negative difference, and we get this difference between the sup of f and ik of f. How do I say that this thing is bounded? Because for every partition, we get different sup and different inf. It's not something constant. I want to write it down that way. Now f is bounded. Because f is bounded, f katan, little f is bounded. There are small m and big M such that fx is bounded between them for every x in A and B. And specifically, the SAP is smaller than M. The SAP is the smallest upper bound. Moreover, it's just the SAP of one little segment, not the whole segment itself. So of course it is smaller than the upper bound M. And on the other hand, the infimum is larger than small m. Infimum is the largest, the biggest lower bound. Moreover, it's a lower bound of just one little segment. M is lower bound for all the segment, probably much smaller. Big M is bigger than sub, and small m is smaller than inf. We have, or we get, that our sigma of oscillations of omegas, which we've already seen that is smaller than the difference between this sub and this inf, is smaller than the difference of big M and small m, because I just, I don't know, say enlarged the soup and just made the infimum smaller. I mean, difference between, for example, 4 and 3 is of course more than the difference between 5 and 2. If the big one is bigger and the small one is smaller, and as we wanted, the sum of all omegas is actually bounded. And bounded is required. So our first proof is done. Of course, I give you place to ask questions. A monotone slash monotonic, whatever function is integrable. Mm-hmm.
Yeah, I think the question is what?
Yeah, I agree with that.
As we said, no, the definition of the definite integral is ugly. Nibor, you say, אתה לא יכול לסבן את זה. You cannot, no, put pretty face on it. It's ugly. It's not the definition of derivative. אתה לא יכול לסבן את זה. You can't put soap on it. Yes, you can't. But it's actually a verb. It's not to put soap on, it's to soap. I don't know if say it in English. לסבן, when you put soap on yourself, it's called to soap in Hebrew. Yeah.
Wait, so monotone function is a function where it's bounded? No.
No, it's always increasing or decreasing.
Okay.
So such functions.
Right. It's monotonically like a series.
Yes, exactly.
Okay, fine.
So such functions are integrable.
Right.
They
Even
do
if it's not
have
continuous.
what?
Even if it's not continuous.
Yes.
Okay.
And continuous functions, that's our B formal are integrable even if they are not monotonic or monotone, whatever.
Okay.
So here we proved that if a function is monotonic, then it is integrable. It has area between its graph and the x-axis.
Right. And the omega, like that's the difference between the infimum and the soup.
Yes, for every little segment along the partition. So that was A. B has the same vibe. I mean, we want to prove and use sandwich and bounding something, but when you go to the details, it is using some different methods. What?
Like, are these to know these proofs is that needed for the exam?
Exercises that uses proofs is what I think is what you said.
Yeah, so as a lecturer, I don't like to put lectures, maybe Eris did it, or some of different lectures you've already had. There are lecturers who like to put one of the questions of the exams, just to be one, just a proof, yeah. Just give you a sentence, some theorem from the lecture, and you know, rehearsing the proof. I don't like it. I mean, if we prove some theorem here in class, you're not going to have to prove it exactly as it is in the final exam. There are going to be proof questions in the exam, not so many. I mean, the exam is still very far, but um, my my favorite exam structure, and that's what I'm going to do to the Hebrew group. And right now we are where you our group and the Hebrew group are at the same level. So right now I'm still planning on giving you the same exam, just different language. I'm and that's what I did in all the last semesters. I taught in F2 on both semesters of last year, both semesters of the year before that. So it's 5 questions. Every question is 21 points. So you add up to 105. And generally speaking, one question is about calculated integrals, which is technical question most of the time, not theoretical, not proof question. Second one is about definite integrals, generalized integrals that we're going to see in lecture 7, 8. Let's see how we go. And then sequences of functions, sequences of series, then calculating some sum or something like with the series, and a question about functions of 2 or more variables. So the questions number 1, 4, and 5, generally speaking, are very technical, not proof question. Find the derivative, find the maximum of some function, etc., etc. The the 2 and 3 questions can be more theoretical, can be more proof questions, but it's not black and white. There are questions that are some technical, some proof, etc., etc.
I just wanted to know this when you do proofs with us, like is that just to understand the reasoning behind the actual thing that we're going to be
No, it's
using?
not understanding because even though I'm not going to put the same theorem in the exam for you to prove, I can put something similar or some, find the counterexample. But if you don't understand the theorem itself well, including its proof, it will be very hard to find the counterexample or stuff like that. So proofs are important, not just for understanding the ideas and the mathematics behind the theorem itself. But yes, the bottom line in order to succeed in the exam, one needs to, even not, writing down all the proofs by himself, to understand what we write. I don't know exactly what did Erez put in your tests in last semester. We didn't talk actually, so it probably was different tests. I for the Hebrew group and you for the English group.
Yeah.
Definitely bad or good?
I think we got it easy.
Okay.
For linear, for calculus, I'm pretty sure.
Yes, my tests last semester were a bit difficult. No, I used to in the last years, it's called Libru to recycle some questions. I mean, a question that appeared in the 2021 test appeared again in 2024, for example.
Complain.
And someone complained is not the right word. Someone snitched. Someone so stupid, he was given a gift. A gift from let's say 5 questions. Every question has 2 sub questions. So it's 10 questions at all. I used to recycle 5 or 6. So any student who studied well to the test, which means solved by himself all the exams from the last 4 or 5 years, was passing the exam automatically. He had 60 points, even more, that he already know how to solve. Of course, these questions were not very easy by themselves. It was easy because you already seen the solution of the question when you studied to the test. And the other 4 questions weren't so bad. So after Moed Aleph and term A and term B, the average grade was above 70, something like that. And considering that in our course, another snitching, by the way, the final grade was composed from your test grade and your homework grade and your midterm exam grade, even though you didn't pass the exam. So there were many students who got their 55, 54 in the exam with no place to give them some any other point, but the homework part and the midterm part of the final grade just pulled them over the 60. And we're not having it in this semester. Adi told me, you know Adi?
Yeah.
Yeah, you know Adi? It's the big math lecturer of the computer science department here in Bar Ilan.
One word from things.
What? No, on the contrary. The big bad wolves of computer science force her to hurt you.
Oh.
Yes, it's like in Egypt when Moses went to Egypt land, etc., etc. So we have the Israeli policeman, which was responsible for the Hebrew working, and the Egyptian policemen, it's called Nogsim in Hebrew, they were beating them. Why don't you? I mean, they're responsible for the work of the Hebrews, so it's the same here. The big bad wolves of computer science, all the professor this, professor that, forcing a D to take the level up and stuff like that. Not her choice to be cool to the students. So we used to recycle every majority of every test from semester to semester. And after Moed Aleph, last semester Aleph last year, or after the 2 terms, Adi called me and she was like, some students told me that some of the questions you just recycle them. It's what the fuck? I mean, it's harder to me. I need to write down a whole new set of 10 questions every test. It's harder to you because they're all new questions. So why the hell would you say to someone who decides, say to each other whatever you want, that I'm recycling questions?
Do you think someone actually complained to her though?
No,
Yeah, of course, of course.
It wasn't like the person just let slip.
No.
Complain.
I don't know if they went specifically to complain about that, but there was. I wasn't there. You maybe know better than me.
So
Do you know this person?
It's irritating.
They will find them. No, I was told I have something to pay.
As far as I understand, as far as ID told me, there was some kind of a meeting between the faculty staff and representative of the students. I guess how it's going, what do you want to improve. So no, some friendly meeting, and they said it negatively somehow.
All of them.
I don't know that the fact that the questions are recycled is bad. No, if the faculty staff says it, I understand. Why do you recycle them? To test them with some new material. It's easy to pass the exam. We need to make it hard, etc., etc. But it came from the students themselves, which is completely, utterly stupid. I really don't understand what's the motivation.
How much do you hate yourself?
I really don't understand. I mean, you know what? I'll use GPT. I look for, other universities' exams. I'll write down 10 new questions every exam. Yeah, it's 5 questions, every question is both to say thing.
You have to ask ChatGPT to give us questions.
Yeah.
Let me just say,
What did you think about the next questions here?
And moreover, that's not their problem. I'm not snitching about it as far as I know, but probably you'll give me some different insights. As I said, the final grade used to be calculated from all the course parts. Doesn't matter what the exam grade was. Now you have to pass the exam in order to activate the homework part of the grade.
and that was recently that they did that.
What?
How recently did they change that? The homework part.
In all the other courses, it was like that for years.
Right.
Yeah. And Adi I don't know exactly how, she found out that I am doing it the whole grade method, which is easier. Because yet again, the grade of the homework grade and the midterm grade, dozens of students throughout the years, along the years, passed Infi 1 and Infi 2 because of that. I mean, it's let's say on the last 4, 5, 6 years, average of more than 200 students per semester. At least 10 of them, Moed Aleph, term A or term B, were on the verge of failing, but the homework grade pulled them through the passing grade. So it's not exaggeration to say that hundreds of people, not thousands, but hundreds of people in the last, I teach Infi since 2018 or now 19. And the last 3 or 4 years, maybe even 5, it is both semesters. One semester is small, spring semester it's called, but it's still dozens of students. A lot of students passed just because their homework grades saved them. And we don't have it this semester. We're going to have it next semesters. Not our recycled questions and not our passing grade with homework. Thanks to some snitching students. You know what snitches get, right? Of course. In Hebrew, it's say, בקב"ן עודר, מלשינים דוקר.
No, like this.
Yeah.
What? Yes.
Yes, exactly.
It's something you need to know when you go to the idea. Okay? It's important.
Now, after listening to the mission, I think we have like 2 minutes left.
Yes. Of course, it's very fun to talk about other stuff than proving mathematical theorems. And yes, 2.5 minutes, we're not going to prove theorem B. I just want to say one thing. We will not prove B, but in order to prove it, one needs the following. Statement about continuous functions. If f is continuous in the segment AB, then for every 2 sequences
Let's call them AN and BN. Contained in AB, we have the following sentence. If the difference between AN and BN tends to 0, then the difference between their images tends to 0 as well. I don't know if Erez mentioned it in Infi Echad, Infi 1. When I teach it, but the last year at least, I don't have enough time to do it. But this condition, this property, if the difference goes to 0, difference between the images go to 0 as well, is called uniformly continuity. Uniform continuity. The function is uniformly continuous. It's a condition, a property stronger than continuity. If a function satisfies that, then it's continuous. Vice versa, it is true only on closed intervals. And we can have a big discussion, 1 or 2 lectures about this property of uniform continuity. We don't have this time, not in Infi 1 nor Infi 2. So we finish here this lecture, and you should remember that continuous function and function with finite number of incontinuities points are integrable as long as they are, of course, bounded. So the theorem itself is, of course, true, but we have a discussion of snitches, and we started 10 minutes late. So it's all good. He was late as well. He showed up here 1 second before you. Not your all fault. All fault. So we can finish here. Hope you have a good rest of the week. And as